Good morning, gentlemen. The purpose of this lecture is a quick and easy guide on how to complete the following review. I will have timestamps listed in the comments of this YouTube video below, so you can skip ahead to each of the subjects that we're discussing, but I'm going in order of how we did it in class. So for example, I'm going to start with electron dot structure, move into ionic compounds, going to the crisscross, do the properties, go over covalent, go over Lewis dot structure, and so on and so forth. So use the timestamps below to help jump you into that video. So if you feel confident about something, you're not reviewing what you already know. So let's get into this. The electron dot structure is what we covered when we just got back from winter break. Now with this, there is a specific order that you're going to put the numbers in, and when you look this up, you might get several different answers, but I like to do it where I put one and I work around clockwise. When you give your electron dot structure though, I will not take points off if you have them in the incorrect area. Just as long as you have 4 by themselves and then you start pairing them up, then you're good. So there is a specific order that you can put them in. I just do it by clockwise, just like this X says. But again, on a test, as long as you give me the correct number of the electron dots and you make sure that once you have more than 4, you're pairing them, you're good. If you're pairing before you put all 4 down, then I will be deducting points. Now, since we had an opportunity to kind of look at that, I want us to practice the electron dot structure. So I will do magnesium, and then you will do the next 3, but I will go over them. So magnesium, I have my formula already written out. So all I need to do is, looking at my periodic table, find how many valence electrons magnesium has. Magnesium has 2 valence electrons. So just like using my figure where they gave me 1, 2, 3, 4, 5, 6, 7, 8, I'm going to put 1 and 2. And that is the correct EDS, so I can move on. So now I would like you to try oxygen, sodium, and chlorine, and then unpause this video when you complete that. I'm going to follow the same steps I did with my magnesium for my oxygen. I need to find the number of valence electrons. I look at my periodic table and I see oxygen is located in group 16. So I'm going to have 6 valence electrons. I do my order, and I prefer to do it like this, but whatever works for you. If you wrote, then you are fine. That is perfectly acceptable. I just like to have it like its little arms. So there's my valence structure for oxygen. Sodium. I look at my periodic table, I see sodium is in group 1. So I have 1 valence electron, and I can just go boop. And last but not least is chlorine. I look and I notice chlorine is in group 17, so it has 7 valence electrons. And there is my electron dot structure for chlorine. So now that we made our electron dot structures, why don't we combine them together to make that ionic compound? So let's notice, how does our EDS react when we're dealing with ionic compounds? So I'm going to make my electron dot structures. For both of them, I think it's a little bit nicer to start off with. You should have these written down in your notes, so that should be a lot quicker for you. Now remember, when I'm dealing with my electron dot structure and ionic compounds, I'm going to see the electrons from my cation, or remember my metal, donate or give to my anion or my nonmetal. Because recall, my metal is always positive and my nonmetal is my negative. So I'm going to see magnesium give an electron to oxygen where it's not full. So the side of my electron where I only have one, not two dots, is it's going to donate that electron. And notice I have 2 electrons for magnesium and I have 2 spots for oxygen. So I should end up with something that looks like Mg positive 2, because I gave up 2 electrons, meaning I'm twice as positive, and I get oxygen negative 2, because now I have gained 2 electrons and I have filled my orbital. So why don't you try and see what would sodium look like when it donates its electron to chlorine. All right, sodium donates its electron to chlorine, and I get something that looks like Na positive 1, and then Cl negative 1, because again, I lost my electron and I gained an electron. Okay, if you're having a hard time with this, please reach out to me and I can give you some more examples, or you can look at the ionic compounds that we've done in Bell work, and that should be able to also give you a couple more examples to work with. Now we are going to get into ionic compound naming and formula review. With this, I am going to be discussing the different types that we see, including Roman numerals, how to do the crisscross, and a lot of that basic information we need to know. Now we're going to go into what's in the name or the formula. So the name is something that's always going to be written out. So for example, up above what I have is calcium and nitrate. So my name is just me writing out the metal in the first position and my non-metal in that second position. The formula is what I gave you above, where instead of writing it out, I'm using the 1 to 2 letters or the polyatomic, and I'm writing it out, and I use that crisscross method. So when I'm doing my formula, that is when I have to do my crisscross. Next is the subscripts. The subscripts are always these numbers that are in my blue here. These tell me the amount of element. So for example, if I wanted to know how many calcium atoms I would have, goodness. So if I wanted to talk about the amount of calcium I had, excuse me, I had some errors there, then I would say, well, I only have 1. I'd have 1 calcium. But if I wanted to know how many Ns I had, or my nitrates, I would take this 2 that's on the outside and distribute it in. And when I distribute that in, I'm going to multiply by that number. So here it's like taking 2 times 1, and I get 2. Next, I need to do my O's, so I'm going to distribute that. But notice my O has a 3. So I'm going to take 2 times 3, and I get 6. When I have parentheses, that is when I'm going to multiply my subscripts. Now, what you need to know is you're only using parentheses with a polyatomic, and you're only going to use that because you're never, and I repeat this, you will never change a subscript on a polyatomic. It is my little group. I want it to stay together, and so I have to use those parentheses. You cannot just go through and multiply the 2 in the formula. You have to write it with parentheses. On a test, if you write it incorrectly, like you go and distribute the 2, so I get CAN2O6, you will lose points because that is incorrect. So you're never going to change a subscript from a polyatomic. You're going to utilize the parentheses. Now we're going to do part 1, which is going from formula to name. This is what we really focused on in our previous unit, in Unit 5, where I'm going to write my metal first. So my metal will always be first, and then I'm going to write my non-metal in that second position. If my nonmetal is from the periodic table, which I'm going to say PT, I'm going to change that ending to "-ide." And if it's from my polyatomic box, I will not change the ending. The ending stays the same. So now having that review, why don't, using your periodic table, we try NABR together, and then you're going to try K2S and AL and O3 on your own. So the first thing I need to do is I need to find what is Na. And if I find in group 1, I find that Na is, sodium. And then I need to identify Br. Br on its own is bromine. Because I'm finding this from the periodic table, I am going to remove my INE ending and change that to "-ide." So in the end, I get sodium bromide. So you try the next two on your own, and then I will go through them. All right, my second one should be potassium sulfide. And my last one will be aluminum nitrate. Remember, I'm not going to change the ending on my polyatomic when I go from formula to name. Remember that your metal, which is your cation, will always go first, and your nonmetal, which is your anion, will always go second. My nonmetal will change to an IED ending unless it's from the poly box, which we just did up there. All right. Now that we've gone from a formula to a name, let's review going from a name to a formula. The goal of this is that your charges should cancel and always equal 0. This is where we use our crisscross. Remember, our crisscross is when I cross my charges over. So I could ask you, what is the formula for aluminum oxide? The first thing I want to do is identify what are my charges. Now, I know my charge copied over here, it should be up here. I'm also going to go through lead oxide, just like we did in the lecture. So I find my charges. My next step is to do my crisscross. So what I'm going to do is I'm going to take the 3 from my aluminum. I am not going to bring the charge, and I'm going to cross that over to my oxygen, and it hops down below and it becomes a subscript. After I do that, I'm going to go to my oxygen. I'm going to cross that over, and it drops down to my aluminum, so I get Al2O3. Now, in the case that I have PB here, I have 4 and I have 2. The 4 for my PB is going to cross over to the 4 for my oxygen, and the 2 for my oxygen is going to cross over to become the 2 for my PB. Now notice I have a 2 and I have a 4. I can simplify this by dividing 2 to get PbO2. Now we did talk about this, and as a reminder, on the test in the short answer section, if you do not simplify, I'm not going to take points off. However, it is good to get in the practice, as you're going to be doing ionic compounds when you're in chemistry next year. But right there is my crisscross rule. If you are still struggling with this, please come and see me. I can have some more one-on-one time to cover it. The beauty about the crisscross is that I can check. So I can make sure that my charges balance out. So I brought that 3, I had my 2. I can go over and I can say if my aluminum has a positive 3 and I now have 2, when I multiply those together, I get 6. And my oxygen is naturally a negative 2. When I cross that over, I end with 3. Do these equal? And in this case, they do. So that's a really good way to check yourself, because remember, we want that net charge to be 0. So now what we just did, I would like you to give the formula, and this is where I'm going to use that crisscross. So I will do aluminum sulfate with you because we will be working with a polyatomic, and you will do lithium selenide on your own. So aluminum has a charge of +3. Sulfate I find for my polyatomic, and I get a -2. Again, I like to go ahead and write down below, my skeleton before I do any crisscrossing. Now, I am dealing with a polyatomic, so that means I have to have parentheses because I will never change the subscript on my polyatomic. Once I have my parentheses around my polyatomic, I am good to go do my crisscross. I'm going to start with the 3 from my aluminum. I cross that to my sulfate, and I drop it below. I'm always going to cross to the element I am not starting with the charge. So in this case, I have aluminum to my sulfate. Next, I have the 2 from my sulfate. I'm going to cross that to my aluminum. So I get Al2SO43. I want you to try lithium selenide on your own. Lithium has a charge of Li +1. Selenide has a charge of -2. Again, I'm going to write my skeleton. I'm going to start with the 1 from my lithium. I cross that over to my selenide. I'm going to get a 1 down there. And next I'm going to take the 2 from my selenide, cross that to my lithium, and I get a 2. All right. The last part that we're going to talk about is the transition metals. Now this is where I'm going to use my Roman numerals. Roman numerals are going to tell me the charge of my metal or my cation. So the 1 from my copper oxide is the charge of my copper. And the 3 on my nickel is going to be the charge of my nickel. Let's do copper oxide together, and then you will do the next one. Copper is always going to be a positive because it's a metal. So I just need to look at my Roman numeral for the charge. In this case, it's 1. Now I need to try and find the charge of my oxide, which is a -2. Now that I have my charges, it's just like before. I draw my skeleton. I take the 1 from my copper. I drop it down to the oxide. I take the 2 from my oxygen. I drop that down to my copper. And here is my balanced ionic compound. You try nickel sulfide, and I will go through it. I need to find the charge of my nickel. It's positive. I look at my Roman numeral. It's a 3. I need to find the charge of my sulfide, which is a -2. I make my skeleton, and now I have my crisscross. I take the 3 from my nickel, move that down to my sulfide. I take the 2 from my sulfide, cross that to my nickel, and I have my ionic compound. Now that we've had a chance to review how to name and give the formula for ionic compounds, let's go over the properties quickly. The properties of my ionic compounds are, number 1, they are completely different properties from the elements it contains. So whatever I'm starting with, so in this case I start with my sodium, metal, and chlorine gas, those are going to have completely different properties compared to my ionic sodium chloride. So a great example is that I have a metal over here, I have a yellow toxic gas, but together I get something I can put on my fries, which is safe for me to eat. The second thing is that they're going to form a crystalline structure. The crystalline structure is an orderly cube of ions, and I have that alternating pattern of a positive and negative, a positive and negative. You can see in the picture I provided that I have that positive and I have that negative pattern going on. I'm not going to have two negatives bond together, and I'm not going to have two positives bond together for this crystalline structure. It will always be a positive and negative, a positive and negative. Next is that I can see some of the crystalline structures with my naked eye. They have those jagged edges, and it looks like something you would find if you'd open a geode. The next property is melting points. Now, ionic compounds are going to have those high melting points. We got a chance to see this in the lab when we researched. Compared to our mystery molecular compound, my ionic is going to have those very high melting points where I can't exactly melt it in my own house, but I could in the lab. Next is solubility. We also got a chance to see this in the lab when I was mixing, and I had those test tubes filled with water. I had a mystery molecular compound and an ionic. My ionic was able to dissolve pretty quickly, and the reason for that is that crystalline structure can break, and the water molecules are surrounding the individual negative or positive ion, limiting them from bonding together. The beauty about this is that dissolving is a physical change. So I can easily get my ionic compound back if I dissolve out the water. And last but not least, we have conductivity. Now, conductivity is when I can conduct an electric current when it's melted or dissolved in water. We had a chance to see this in the lecture. You can look at it in this video if you are curious, but they are good conductors of electricity, which makes sense because they have that metal component. Now we're getting into covalent compound naming and the formula review. Again, this should mainly be a review for you, which is great, but I will get into some other information as well. The first thing that you need to recall is when you're working with a covalent compound, when you draw the electron dot structure, your electrons are always going to be shared. You're not going to see that jump or donation that we see with the ionic, so make sure that you understand that you're going to be sharing, whereas when I'm working with ionic, I see that donation, so I'm donating my electrons. Now, sharing will only occur between my unpaired valence electrons. The exception of this, hydrogen will only need 2, where the other ones will have 8. An unpaired electron is always going to be shown on its own. And so I would add another electron to pair that. So if you're looking for unpaired, it's going to look like this. Paired electrons are going to look where there's 2 of them on one side. With covalent naming, we discussed this in Unit 5, so when I name, you're always going to use those Greek prefixes. Those Greek prefixes, as a reminder, are mono, di, tri, and so on. This will give you the ability to go from a name to a formula, because if I give you N2O, you're able to say, well, my prefix has to be di because I have 2 N's here, and then I do nitrogen, and because I only have 1 oxygen, I'm going to put mono in front of my oxide. So that makes it a lot easier, but we did practice this in class, and if you have any questions, please let me know. But naming is not that difficult with this. Here are those prefixes as a reminder. I do have those half sheets, but I recommend, I will have this on your test, along with a bigger polyatomic ion box, but make sure that you do understand how to read these. Now that we've had an opportunity to kind of go through a review, I would like you to try the following. So what you are going to do is, if I give you the formula, give me the name, and if I give you the name, give me the formula. Pause this video, and then I will move on. All right away I have 1 carbon. Now 1 in the Greek prefix is used as mono, but I never have to write mono for my first element. So I'm going to write carbon. And then I'm going to look at where my oxygen is in the amount. I have 2, so I'm going to use the prefix di, and I do dioxide. I still need to do my IDE ending, just like ionic when I'm naming my covalent. Now that we've named one, which should feel like review, the backwards is just picking out the information. So in my first one here, oopsies. Oh goodness, there we go. In my first one, I'm dealing with nitrogen. Because I don't have a prefix in the front, I'm dealing with 1 nitrogen, but because I don't need to specify, I'm doing N, and then I have 1. The next one is tri, so I know I have 3 in my next element, and it's hydride. Hydride is hydrogen, so it's 3 hydrogens. I don't have to write the 1, so I could put NH3, but I will accept both. Next, I'm going to do my nitrogen, so I'm still dealing with nitrogen, and my prefix is di, meaning I have 2, so I put A2. Dealing with tri again, oxide is my element, so I put O3. And that is all it takes for going from name to formula and formula to name with covalent. Now we're going into Lewis structure review, which is electron dot structure, but make it covalent. So let's get into the steps for that. So Lewis structures with covalent compounds, it's still electron dot structure, but we have that fancy terminology now. So now you're going to see what is called lone pair or paired electrons. These are where I have my valence electrons from my first element, and I already filled up that one side. So these are considered paired, and they're non-bonding. Covalent bond is when I have unpaired valence electrons shared in a bond. So my unpaired is with a line, and my paired is with my dots. The things you must complete when you're doing this is you must find the formula mass, which is just adding up my atomic mass. So it's just taking the number, that's the decimal, and multiplying by the number of element, and then adding your compounds all together. After you do that, you want to find the total number of valence electrons, and then you want to find the center atom, which is my most unpaired electrons. So why don't we do an example? So we're working with CH4, so using my periodic table, I want to find the formula mass. The number for my carbon is 12.011, and I'm going to be adding that with 4 hydrogens. Hydrogen's atomic mass is 1.008. So I'm going to do the math, add those together, and I should get 16 AMUs. Next, I'm going to find my total number of valence electrons. Carbon has 4. I can see that with my periodic table. And hydrogen each have 1. But because I have 4, I'm going to multiply that by my 1, and I get 4. So 4 plus 4 means I have 8 total valence electrons. Now I need to find what would be my center. So what I like to do is I like to draw my electron dots, and whichever one has the most unpaired electrons will be considered my center. In this case, it's going to be my carbon, because carbon can have 4 bonds, whereas my hydrogens all have 1 bond. So that is going to bond with my carbon. All right, now that we've done one together, why don't you try one on your own? All right, so try this one on your own. Find the formula mass, the total number of valence electrons, and which one you think is the center. First, I want to find my formula mass, so I'm going to go and find my hydrogen atomic mass, and I'm going to multiply that by 2 because I have 2 hydrogens. Next, I'm going to find my oxygen, and and I'm going to add these together and round to my nearest whole number. I should get 18 AMU. Now I want to find my number of valence electrons. Hydrogen only has 1, meaning I'm multiplying that by 2 to get 2 total. And my oxygen has 6. So 6 plus 2 gives me 8. Now I want to find my center. I'm going to start with my oxygen, 1, 2, 3, 4, 5, 6. And I have my 2 hydrogens. In this case, my oxygen will be my center because I can support 2 bonds. And just like previously, my hydrogen can only have 1 bond. So my oxygen is my center atom. If you are curious as what that would look like, it would look like this. All right. Next, I would like you to try PCl3. This one will be a little bit more challenging, especially when we take the atomic mass. So try this on your own. I want to find my atomic mass, so I find that my P is equal to 30.974. I'm working with 3 chlorines, so I'm going to have 3 times 35.453. I put that in my calculator, I add them all together, and I get 137 AMU. Next, I want to find my total number of valence electrons. Now, I'm going to be adding all of my numbers together. P has 5 valence electrons, and I only have 1. And my chlorine has 7. Now, I do have to multiply my 7 by 3 to give me 21 total valence electrons for chlorine. I take my 5 from my P and add that to get a total number of 26. Now I want to find which one would be the center. So I draw my electron dot structures, and now I'm going to see which one has the most unpaired electrons. In this case, it will be my P, because I can form 3 bonds where my chlorines can only form 1 bond. Again, if I want to draw this out, I would get something that looks a little bit like this. There is my final answer. Now we're moving into balancing chemical equations review. As a reminder, here are my chemical equation basics. I'm going to have my reactants, and I'm going to have my products. My reactants are always my starting material. It's what is going to be on the left of my arrow. My products are always going to be what I produced, what I end up with, and that will always be on the right of my arrow. My left of the side is like what I would begin with the lab, and what I end up with would be on the right. So an example is when I look at table salt, it started as sodium plus chlorine. And when I combine them, that's when I get my NaCl, or my sodium chloride. As a reminder, my coefficients versus my subscripts are extremely important when balancing equations. I'm always going to have my coefficient as the larger number in front, and that will give me my number of molecules. So that is the one that I'm always going to end up distributing when I balance. My subscript is just the number of specific atoms in that molecule. This is the number I get when I do my crisscross. Balancing is always going to be used with coefficients. You will never change a subscript when you're balancing your different equations.
The law of conservation of mass is an extremely important concept you need to understand and the reason why we balance. Matter cannot be created or destroyed during a chemical reaction. So that means the total number of atoms will never change. My number of atoms on the reactant side has to equal my number of atoms in my product side. The total mass of the reactants will also equal the total mass of the products. So it's extremely important you understand that if I have a certain amount on one side, for example, if I have 64 grams of calcium, the calcium in my calcium carbonate will also have to be 64 grams. And in my zinc carbonate, if I have 192, you can do a little bit of backwards math, but I will have the same amount of carbonate on both sides and the same amount of zinc on both sides. So that's why it's important you balance your chemical equations. The total number of atoms of your reactants will always equal the total number of products. So if I wanted to, I could put this in a table, and I could say if I'm working with my H, just my H. There we go. So if I'm working with my H, I have 2 on my reactant side and 3 on my product side, and I'm seeing that when I'm looking here. If I'm working with my N's, I have 2 on my reactant side and 1 on my products. Right away, these are not equal. So I need to balance these so that they are equal. So what I'm going to do is I see I have 2 hydrogens on my left side, I have 3 on my right. I'm going to find the lowest common denominator between 2 and 3. This is equal to 6. So now I'm working backwards and I'm going to say 2 times what equals 6? Well, 2 times 3. And 3 times what will equal 6 is 2. When I do this, notice in my compound, the 2 is now going to be distributed to my N, giving me 2 N's on my product side. This now results in having an equal and balanced chemical equation. So now I am following my law of conservation of mass and I am good to go. Next is types of chemical reactions. Now, you're going to be really focusing on the first 4, but I believe it's important you understand what a combustion is in case I ask you about that. I'm not sure why this messed up, but the first type of chemical reaction we're going to see is our synthesis reaction. Our synthesis is always our combination, and it's where I start with 2 items on one side and I end with 1 on my product side. Decomposition, however, is opposite of my synthesis, where I start with 1 and I end with 2. These are extremely easy to follow because you're either starting with 2 and ending with 1 or starting with 1 and ending with 2. So combination or synthesis is when I'm combining 2 individual elements, and decomposition is when I'm taking apart or breaking apart a compound. We're going to get into more detail about the differences between single replacement and double replacement below. But as a reminder, combustion is important to note because I'm always going to see these as my products. I briefly talked about this above, but remember, synthesis reaction is where I'm only going to see that one product. Decomposition is where I'm only going to see one reactant. So I will have 1 of something on either side of my arrow in synthesis or decomposition. Single replacement is my date-stealing reaction. This is where I'm going to have a single or lone element on both sides. Notice here that I'm starting with Fred and Wilma, and I have Betty on her own. But once I move past my arrow, Betty and Wilma switch sides, and so now Wilma is on her own. So you're going to see a lone element when you're working with single replacement. Like when you break up with your girlfriend, you're all alone. The last one is double replacement. Now, double replacement is when my cations and my anions form and they switch partners. So I'm going to see 2 of cations and anions, but I'll see that switch. So for example, on my left side, I have Fred and Betty, and I have George and Wilma, But now my anions switch spots when I go to the right of my arrow. So now I have a new cation and anion and a new cation and anion. This is an extremely easy one because you're going to see two types of compounds, but you're just going to see the cation switch or the anion switch. Now, what I recommend doing is going through this video again, trying the examples. I do have the slides up on Canvas for you, but please ask me if you have any questions. I hope you have a wonderful day. Bye.